All right, guys, I'm going to go over, wait a second, where am I here? Classwork. I'm going to go over the work due today, parts per million business. Some of you emailed it to me. And let's see, where the heck is it? Here we go. 7 of you have turned it in. So by the time I post this, you should all be done with it. So I'll do this first. This one here, and then I will do the others. So I'll do this kind of fast, so I don't spend 15 minutes on the video. But I know some of you. I know I'm probably going too fast on some of these videos for some of you. So here we go. Now remember, and I'm going to use a smaller. Oh, let's use this color. Looks good today. I'm going to go real small over here. So remember, the equation is parts per million equals grams of solute. So mass of solute, what's being dissolved, and grams of solution, which is the whole solution. Like salt water, the water and the salt, the whole solution would have a mass. All of that times a million, 1 times 10 to the 6th. All right, so there is the equation we're going to use for all 3 of these. I'll have to redo this for 3, but here's how we do it. So a solution with a mass of 5,000 grams, so the solution's mass is 5,000, that goes on the bottom, contains 0.20 grams of NaCl, which is a solute, which goes on top. What's parts per million? What is the solution concentration in parts per million? This one's pretty straightforward. So parts per million, X equals, or you could write ppm equals 0.20 over 5,000. We're going to divide that and then multiply by a million. 1 times 10 to the 6, or 1 with 6 zeros. So if we do that, all right, we get 0.2 divided by 5, 1, 2, 3 equals 0.000, 4 zeros and a 4 times 1 million. And I get 40 parts per million, which is really high for most things, but I made this up off the top of my head kind of, and it's just salt. So if you had a salt solution, that's not the end of the world. It's not like it's lead or mercury or arsenic or something nasty. So anyways, that's the answer. And I need to see the work. So some of you who I've looked at some of them, you have shown some work. That's good. Label units, put a box or circle. All right. Solution containing 0.075 grams of Pb plus 2 ions is found in a sample of river water. If the mass of the sample is 6,500 grams, calculate the concentration of lead ions in the river water sample. So my 0.075, that's my solute. All right, that's dissolved in the water, and this is my solution. SOLN is solution. So I know my mass of solute, I know my mass of solution. I got to calculate for ppm again. Same setup. X equals, this goes on top, 0.075 grams over 6,500 grams times a million. So we got 0.075 divided by 6500. I get 0.0000. So 4 zeros, 1154 times 1, 2, 3, 1, 2, 3. I'm using my phone here. I left my good calculator at school. 11 point, and there's no sig fig rules here, so I'll just do 3. 11.5 parts per million. All right, so that is a little alarming. If you had a river water, that's crazy high for lead. 1 part per million is better. I don't know the EPA limits and standards, but I know it's not 11.5. I would guarantee that. So anyways, that's okay. Again, the point is, can you practice showing the work and getting the answer, right? So that's a concentration of 11.5 parts per million. All right, so there's 1 and 2 on that. Let me kill this and let me do 3 and 4 now. All right, so we got 3 and 4. Here we go. All right, so I'll kind of squeeze it up there so I can do both. All right, so sample of water from, and again here, I'll put it over here. ppm equals grams of solute over grams of solution times a million. All right, times a million. All right. If a sample of water from a local well has a mass of 1 times 10 to the fourth grams, so the water sample has a mass, that's this. That's the entire solution. It has a fluoride concentration of 1.5 parts per million. So now I'm giving you the parts per million. What is the mass of F minus? That's your solute. F minus is solute. That goes on top. All right. So we want to know this number. I give you parts per million. I give you solution. We want to know the solute. So in this case, it's 1.5 equals X over 1 times 10 to the fourth is 10,000. And now this is again times a million. And this is the one yesterday. It's a little bit harder. I think it was Ryan. Somebody said this one's harder. I get that, right? So basically what you need to do is this is how I do it. There's other ways to do it. This is just how I do it. So hopefully it makes sense. I'm not going to show you two different ways to do it right now just to be more efficient here. But I'm going to get rid of the million by dividing by a million, then divide this side, right? Whatever you do to this side of the equal sign, you do it to this side. So if I divide this by a million, that cancels this out to 1. If I divide 1.5 times a million, I'm moving that decimal 6 places to the left. So if we do 1.5 divided by 1 million, so I'll rewrite this over here. I get 0.12345. 1, 2, 3, 4, 5. Oops, no. 1, 5. So that's how many zeros I got, right? Yep. That is this calculation. And that's equal to X over 10,000. So now, this is really over 1. I just cross multiply 10,000 times that number times 10,000. And X equals 0.015 grams of F minus. That's the answer to number 3. Okay. 4. Sample of water nearby lake has a mercury concentration 0.005. That goes here. Sample is analyzed in a lab. It is determined that the amount of mercury in the sample is 0.25 grams. What is the mass of the sample of lake water? All right. So ppm, I gave it to you. The sample is analyzed. The amount of mercury in the sample is 0.25. That's your solute. Sorry. That's your solute. So that goes on top. So it's 0.005 equals 0.250 over X. We are looking for the mass of the sample of lake water. The whole sample itself is always going to be that solution. So there's that times a million. All right. I'm going to do the exact same thing I did up here, except instead of solving for the top of the fraction, I'm going to solve for the bottom, right, the denominator. But you don't need to know all the terms. The point is you're going to get rid of the million by dividing it by itself. That cancels out to 1. Divide this side by a million. So 0.005 divided by a million is 0.123456125. And I'll double check that here. But it's 6 decimal places to the left. Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9. 5 times 10 to the negative 9 is what that is. 5 times 10 to the negative 9 equals 0.250 over X. This is really over 1. Cross multiply. So this one's a little harder because it's going to be this number times X equals 0.250, right? So I'm going to use the scientific notation. 5 times 10 to the negative 9 times X, right, equals 0.250. Now I divide by this number. Oops. 5 times 10 to the negative 9. That cancels out to 1. Now I'm dividing 0.250 by 5 times 10 to the negative 9. X is going to equal this. So 0.25 divided by 5 times 10 to the negative 9. See my this is, I have to rotate sideways here. Hold on. 0.25 divided by 5 raised to the negative 9, and I get 50 Okay, so I should have thought this through. I guess I didn't. So this is 50 times 10 to the 6 grams. 50 million grams. That's a little bit silly. So, yeah, I didn't take that into account. So that's not, or 5.0 times 10 to the 7th. So I'm more concerned with you guys being able to set it up actually, but I should have thought that through as I was doing this. I knew that was going to be big, but so there you go. I don't think I'm off by a decimal there. Let me make sure. Oh, maybe I am. Cell phone calculators. Sorry, guys. Divide by 5e to the negative 9. All right. I think that's right. All right. Yeah, that's right. All right. So there's that. Let me kill that. All right. Let me go back here. What's this one here? All right. So, you know what? Here, I'll do this. All right. State. Oh, you know what? You guys can't do those. We haven't learned that yet. So if you did those or you were confused, I'm sorry. I should have told you just 70, 71. Let me see here. What did I actually put in there? Ay. Sorry, guys. All right. No. Let me look at the assignment. Do only circle. Oh, good. I did say do just circled. All right, good. Okay. All right. State how increase in water temp of the fish tank affects solubility of oxygen in the water. So this is actually review for solubility, that table G stuff with those curves going up or down. So if you increase temperature on the water, the solubility of gas will decrease. It decreases. All right. It doesn't really tell you that in here. Okay. But again, this is a table G, real quick review here. You go to table G. All right. Here we go. Table G. Come on. Right. So HCl is a gas, decrease. NH3 is a gas, decrease. SO2, decrease. The higher the temperature, the lower the solubility, the less will dissolve. Okay. The higher the temperature, the less gas will dissolve. Okay. So warmer water, there's less dissolved oxygen. That's the moral of the story there. Okay. All right. Here we go. 71. Determine if the DO concentration, dissolved oxygen, is healthy for fish. The response must include correct numerical setup in parts per million, calculated result. So work, answer, and then tell me if it's safe. All right, here we go. So we go up here. It says a student's fish tank contains fish, green plants, and 3,800 grams of fish tank water. So this is a big deal. We need that number. 3,800 grams of fish tank water with 2.7 times 10 to the negative 2 dissolved oxygen. That is also a big deal. We need that number, right? So why? Because we want to know the dissolved oxygen concentration in parts per million. So the DO concentration is how much dissolved oxygen is DO. So there's your DO. How much dissolved oxygen is there in a certain amount of water? We're going to do parts per million. So this number here, that's my solute. That goes on top. This is my solution mass. It goes on the bottom. This divided by this times a million. So here we go. So parts per million, parts per million equals 2.7 times 10, what was it, negative 2, I believe, negative 2. Or what you could write there is 0.027. Either one. You guys probably like that better. Divided by, so either number, all right, that's not multiplication. I'm going to erase that. 2.7 times 10 to the negative 2 divided by was 3,800, right? Yeah, 3,800. 3,800 is the whole sample mass times 1 million. And that equals, here we go. So we're going to go 0.027 divided by 3,800. And I get 0.0000711 times a million. And I know where this is going. Yeah, 7.1 parts per million. So there's the first tick, second tick there, bullet. Now this third one. Is it safe? Is it healthy? Well, up here it says health of fish depends on a dissolved oxygen between 6 and 8 is best for fish. 7 is right in the middle. So yes, it is safe. Yes, it is healthy is what you would say. All right, so there's that. All right, back to this. All right, so I love how I said circle and then I circled the whole thing, right? All right, so we'll do this one and then I'll go over the next one, which is a multiple choice, and then I'll stop recording since this is long. All right, here we go. All right, Lewis dot electron diagram for fluoride ion. Well, fluorine has fluorine has 7 dots. 1, 2, 3, 4, 5, 6, 7. That's F, but F minus gained 1 electron. F is 2-7, F minus 2-8. Okay. Here we go. I feel like I need to show everything, explain everything here. Hopefully that isn't annoying for you guys here. So there we go. F is 2-7. F minus 1 would be 2-8. Okay, back to this. So if it gained 1, now it has 8 valence electrons. So 8 dots. You need that minus 1 though. Okay, tin 2. So tin 2 fluoride. Tin 2 means Sn plus 2. That's what that means. Fluoride is F minus 1. I just talked about it. I need 2 of these to balance this out. SnF2. How many parts per million are present in the analyzed sample? And then is it safe to drink? All right, so you know what? I'll do the work down here. Here we go. So if it exceeds 4, it's no good. So here we go. The town hired a chemist. Chemists determined that 175-gram sample of the water, so there's my solution, contains 0.000250. There's my solute. So this number divided by this number times a million. So down here, we got parts per million equals 0.000250 grams divided by, what the heck was it again? 175. 175 times a million equals, here we go. It's all right, bear with me again. So 0.00025 divided by 175 times a million, and I get 1.43 parts per million. Is it safe? Yes, because it's less than 4. It is safe for them to drink. Okay, plan is being developed. So you got to wear goggles, apron, glove. One additional precaution that should be included in the plan. Any of the safety stuff we talked about earlier in the year. So you got gloves on, an apron, and goggles. I've had kids answer, put a face shield on, wear, protective gear on your legs and your feet, like wear boots. Don't wear open-toed shoes. Tie back your hair. Make sure you don't have clothes that are loose and hanging off you, stuff like that. All right, moving on. And the last one here. Here we go. This one. All right. Here we go. All right, so I'll have to just do the work like right over the top. Maybe we'll use a bright red one here for this. Okay, what is the total mass of solute in 1,000 grams of solution having a concentration of 5 parts per million? You know what? I'll do it right here. All right, what is the total mass of solute in 1,000 grams of solution having a so 5 parts per million? Remember, it's ppm equals grams of solute over grams of solution times a million, right? Okay. So the 1,000 grams goes on the bottom. Part 5 goes here. We'll look X here. So here we go. We're going to go 5 equals X over 1,000 all times a million. Okay. Divide by a million. Divide 5 by a million. So I'm going to get 0.1234 and a 5 equals x over 1,000. This is really over 1. Cross multiply 1,000 times that number. X equals, so we move it 1, 2, 3, 0.005 grams. So the answer is number 1. There we go. That took me a while, but hopefully you guys are watching these and it helps you learn the mistakes you made and helps you figure this out a little bit better. All right, here we go. I'll kill this now. How long was it? 20